So I'm going to talk about some work on cosmic rays that's very relevant to Professor Parker's legacy. I'd like to acknowledge some of my current and former students. Chad Bustard is graduated. Rourke Habiger and Evan Hines are still working with me. I'm sure everyone has already given tributes to Professor Parker, but I'd like to give mine. When I started in this field, not only were magnetic field effects left out of most astrophysical calculations, but it was even sort of a joke. After a talk, sometimes someone would raise their hand and say, "What about magnetic fields?" And everyone would laugh. And I think this was, at least in part, because people thought that magnetic fields were very arcane and difficult. But so I really credit Gene Parker with being the one who moved plasma effects, including magnetic field effects, into the mainstream. And he was able to do this, although he was not the only brilliant scientist working on magnetic fields, but he had a unique scientific style that just combined physical reasoning, analytical math, and the ability to distill issues really to their essence, not just scientific issues, but academic and sort of infrastructure issues too. I heard him many times. And he had, an unbounded curiosity that just led him to consider many different problems. And he left his mark everywhere on every problem that he touched. There are so many equations and processes named after his work on these problems. And as I said, I'm going to focus on cosmic rays. So here's the plan of this talk. I'll just review a few salient properties of cosmic rays. Then I'll talk about cosmic ray propagation in the interstellar medium. And then I'll focus on what is known as Parker's instability. And then I'll talk about some unsolved problems having to do with the instability and the wider role of cosmic rays in astrophysical systems. So here are cosmic rays at a glance, everything I'm going to say. So they're the relativistic charged particle component of interstellar, circumgalactic, and galaxy cluster plasmas. They have a broken power law distribution over many orders of magnitude in energy. They're essentially collisionless, but because they do undergo collisions and radiative losses, we can observe them in galaxies throughout the universe. So let me say a little bit about how I chose the title of my talk. We now understand that they exchange energy and momentum with the ambient thermal gas through scattering from kinetic scale fluctuations. And by kinetic scale, I mean the gyroradius scale of the cosmic rays. So those are the microscales in the problem. And because the microscales are on scales below the size of the solar system, and we'd like to describe galaxies and galaxy clusters, we need a fluid theory. And the fluid theory describes the role of cosmic rays in global instabilities, which is what I'll be focusing on today, the heating of interstellar and intercluster gas, the quenching of star formation, and the launching of outflows on galactic scales. So those are the macroscales. So the underlying theme of my talk is the connection between the micro and macroscale processes. But I'd like to stress that although there's a lot of work going on cosmic rays, from fundamental physics to simple modeling, there are just many incomplete aspects of the picture that I'm going to describe, and I'll mention a few of them at the end. So here's the cosmic ray spectrum. These features are known as the knee and the ankle. I like plots like this because it shows you the wealth of experiments, different experiments at different energy ranges that have gone into fleshing out the cosmic ray spectrum. So they're mostly protons. Only 1 to 2% of cosmic rays are electrons. In the Milky Way, the energy density is about 1 eV per cubic centimeter, which is similar to the magnetic, thermal, and radiation energy density in the Milky Way. but the number density is tiny. The mean density of interstellar gas is about 1 per cubic centimeter. For cosmic rays, it's about 3 times 10 to the minus 10. So there's extreme energy inequality in the interstellar medium. Although the spectrum, as you can see, extends to enormous energies, the average energy is a few GeV, so mildly relativistic protons. And the very highest energy cosmic rays have such a large gyroradius in the galactic magnetic field that they're not even confined. And presumably they have an extragalactic origin that we still have not identified. So to summarize, a lot of great work, some of which occurred around Gene Parker at the University of Chicago in the 1960s. What we now think is that cosmic rays are accelerated from the interstellar medium in events, which are probably supernova remnant shocks, that produce a rather hard spectrum, an e to the minus 2 spectrum. But that spectrum is steepened by energy losses and which depend on energy, and escape itself depends on energy. They're confined at GeV energies, they're confined to the Milky Way for about 20 million years, and they're scattered up and down the magnetic field lines of the Milky Way with a mean free path of about 1 parsec. And it takes about 10% of the 1% of supernova energy that does not come out in neutrinos to maintain the cosmic ray energy density in the Milky Way in a steady state. And we've detected cosmic rays, both the hadronic and the lepton component, in star-forming galaxies with a huge range of sizes, ages, and levels of activity. So it seems to be a fact of any galaxy that's forming stars that it also forms cosmic rays, probably from the supernovae. So understanding how cosmic rays propagate in the galactic magnetic field and how they have an effect on the underlying medium is the multi-scale problem par excellence. So here on the left is an image actually of M31, our closest Milky Way-like neighbor. And I've sketched in a tangled magnetic field and cosmic rays random walk up and down these magnetic field lines. And as they random walk, they also spiral. And the average cosmic ray gyro orbit is about this size when projected on the solar system. This is 1 astronomical unit. So we can take 2 things away from this plot. So one is that even if we had an exact representation of the galactic magnetic field, and I believe after hearing Rainer Beck's talk, hello Rainer, that given 10 more years, you could give us an exact representation of the galactic magnetic field, but we could still never integrate enough cosmic ray orbits with all the processes. And so we need a statistical description. And one of the earliest statistical descriptions was due to Gene Parker. And the other thing we can take away is that to develop a fluid theory that allows us to incorporate cosmic ray effects into global models, we can't just use a theory that describes an ordinary fluid, even an ordinary relativistic fluid. It's collisionless, it's non-Maxwellian, and the only reason we have a hope of doing this is that the cosmic rays are nearly isotropic in directions. So we can still do a kind of frequent scattering approach that I'll say more about. So here is the equation that Parker wrote down, although I think not in his original notation, but this is known as the Parker transport equation. And let me unpack the ingredients for you. So N is the phase space distribution of cosmic rays, and it's the isotropic part of it. It's the part that depends only on momentum, not the direction of the momentum. And it's a function of position and time. And it describes advection and compression by a fluid flow. So U is the velocity of the thermal gas. It describes diffusion along the magnetic field. So this is a tensor diffusion, and it's essentially zero perpendicular to the magnetic field. It includes diffusion in momentum space, that's represented here, and it allows for sources and sinks. So it's a very general equation, but as I'll come back to in a moment, there is one theory, which I think is a pretty viable theory, that has an additional term or two. So field line geometry, so the statistics are here in the diffusion approximation, and field line geometry appears through the anisotropy of the spatial diffusion. So you have to know what the magnetic field is to solve this equation in a particular system. So now let me say a few words about how cosmic rays interact with thermal gas mediated by magnetic fields. So the perpendicular dynamics is actually straightforward. Cosmic rays have no inertia to speak of. So perpendicular and parallel mean with respect to the magnetic field. So in a steady state, their pressure gradient balances their Lorentz force. Jc is the current density of the cosmic rays. The Lorentz force on the thermal gas is the current in the gas crossed with the magnetic field. So how do you tell these two currents apart? Well, you don't really have to, because the current in the gas is the total current minus the cosmic ray current, and the cosmic ray current is given by the perpendicular pressure gradient. So we can account for the Lorentz, we can essentially substitute the total current, for which we know from Maxwell's equations, for the gas current, and include the perpendicular cosmic ray pressure gradient. So this is kind of a sleight of hand, but it puts the force equation for the thermal gas in a very recognizable form. But the parallel dynamics is a little more subtle, and it depends on a phenomenon called gyroresonance scattering. So this red line is a magnetic field line, which has large scale curvature and tiny scale wiggles. And this black helix is the orbit of a particle. And you can see that it follows the field line pretty well. And these tiny scale wiggles, which are smaller than a gyro radius, kind of average out over the orbit. But if you put in a wave such that the Doppler shifted frequency of the wave is the cosmic ray gyro period, you get a very strong resonant interaction. It's like a resonant harmonic oscillator, and it leads to a diffusion coefficient, which you can estimate kind of geometrically by saying that the fluctuation, which has amplitude delta B over B, gives you a delta theta of the same size, and the mean squared delta theta divided by a time, which we take to be the gyro period, gives us a scattering frequency. And in the classical theory, these waves are considered to be Alfvén waves with the speed very small compared to the speed of light. So they have a rather small electric field. And so the change in particle direction is relatively large compared to the change in particle energy. Now, there are two theories for the sources of these waves. So there's the so-called self-confinement theory, in which the cosmic rays generate the waves through a kinetic instability. And this has the fluid theory that corresponds to the self-confinement model is what we could call classical cosmic ray hydrodynamics. But the waves could also be present as just part of the interstellar turbulent cascade, which you saw on 50 parsec scales in Rayner-Beck's talk. And in that case, the confinement is by extrinsic turbulence, and this gives you a kind of generalized cosmic ray hydrodynamics, and you can smoothly bridge the transition between these theories. So let me just flash up here the growth rate for this kinetic instability. There's, so F is the cosmic ray distribution function. This is the gyro resonance condition. There will generally be fewer cosmic rays at increased momentum. So this term damps the wave. And the reason I put this up is to show you that even a very small anisotropy is multiplied by a very large factor. V is essentially the speed of light it's the speed of the cosmic ray, and omega over k is the Alfvén speed. So an anisotropy of order VA over C, which is maybe 10 to the minus 4 in the interstellar medium, will give you an amplification of these waves. It's it requires very mild conditions for excitation. And fortunately, this formula can be boiled down to something much simpler. The growth rate of the instability is a constant of order unity times the proton gyro frequency times the ratio of the cosmic ray density to the thermal ion density times this drift anisotropy. And neutral stability is when the drift velocity is the Alfvén speed, which means that the cosmic rays are isotropic in the wave frame. You can multiply this, you can find the back reaction of the scattering process on the zero order distribution function by going to next order in perturbation theory, derive a so-called Fokker-Planck equation. So this bracket here is an average over randomly phased waves. This is the electric field associated with the wave. This is the perturbation of the distribution function caused by the wave. And miraculously, this miracle has been known for a long time, this boils down to a diffusion operator. So now we're making contact with the Parker transport equation. The main component is actually pitch angle scattering. The scattering frequency is what we derived on heuristic grounds. And there is some Fermi acceleration if you have waves traveling in both directions. You can multiply the Fokker-Planck equation by particle energy and integrate over momentum space to derive an equation for the flow of energy. UC is the energy density in cosmic rays. This is the energy flux. And this term on the right-hand side represents energy transfer to waves. And it looks sort of useless in the form in which I've written it. But if you make the approximation that the waves, that the scattering is frequent, so this is what I meant by near isotropy, then you can go back to the equation for the components of the diffusion tensor and the growth rate, and you can show that this right-hand side is just this term that looks like friction. So it's the Alfvén speed dotted with the cosmic ray pressure gradient. And so what this says is that the energy density of cosmic rays is minus the divergence of the energy flux of cosmic rays, just kind of a normal conservation law for energy, but there's this frictional coupling to the background. You can go a little further. So the anisotropy will not necessarily be right at threshold. It has to be slightly above threshold because of some damping process. You can balance growth and damping, and you can find the steady state value of anisotropy. And what seems to happen for the Milky Way, no matter how many damping mechanisms are considered, is that the self-confinement theory works up to a couple of hundred GeV. And then above that, the damping of the waves is much stronger than the growth rate of the waves. And so the anisotropy is so large that there has to be some other source of waves to confine the cosmic rays. And so there's a transition from self-confinement to extrinsic confinement, most likely around a couple of hundred GeV. So here's a summary of what I just said. The cosmic rays exert a force on the thermal gas. They heat the gas at this rate. You can show that there's a sort of polytropic index for the cosmic ray fluid, where their pressure is proportional to the gas density to the adiabatic index over 2. So this is 2/3 for relativistic fluid. This is constant on magnetic flux tubes. In the confinement by extrinsic turbulence, generalized cosmic ray hydrodynamics, there's no streaming relative to the gas, and there's no heating. So the case that Parker wrote down is really more like the extrinsic confinement case. And implementing this numerically is tricky, but there are at least 3 schemes out there for doing it. And they've been implemented in a variety of codes. And they're being applied to gas dynamic problems in galaxies and beyond, in the circumgalactic medium and in the intra-cluster medium. So now I'd like to focus on one particular problem, which is the global instability problem, and that is Parker's instability. So Parker considered the vertical equilibrium of the galactic disk. This is something of a review from what Rainer was talking about before the coffee. And so here's a sketch of the distribution, the density of thermal gas perpendicular to the galactic plane if there's no magnetic or cosmic ray pressure support. And here, if you take the same amount of gas and put in some magnetic and cosmic ray pressure support, you lower the density in the midplane and you kind of puff out the gas layer and increase the effective scale height. So this means that there's a source of free energy in a system which is partially supported by magnetic fields and cosmic rays, because the magnetic fields and cosmic rays have no inertia. They're not tied down by gravity, and the gas is being suspended above its natural scale height. So that is your free energy source for driving instability. And here is a sketch of the outcome from Parker's original paper. So this is a little more polished than what he wrote to Rainer back in the letter. But here are the field lines. Gas has collected in these dense pockets, and the magnetic field has risen above where it was originally. So this will only happen if it takes less work to compress the gas in the valleys than was released by lowering the gas in the galactic gravitational field. So the prevalence of the Parker instability depends really on how compressible or incompressible the interstellar fluid really is. So here is a quantification of these arguments, also in Parker's 1996 paper. He considered a model which has become kind of the default model for studying this problem, a model in which the ratio of magnetic to thermal gas pressure is independent of height, and the same is true for the cosmic rays. So here is the effect of magnetic and cosmic ray pressure support on the thermal scale height of the gas. And he showed, using perturbation theory, that in order for this system to be stable, the adiabatic index of the gas, gamma sub g, has to be greater than this quantity. And basically, it always is. It is always unstable unless the gamma for the gas is much greater than 1. And he argued that gamma gas was actually 1. Now, in 1966, when Parker published this paper, the work that I just described on cosmic rays coupling to the thermal gas had not yet been done. So Parker modeled the cosmic rays as just particles moving at the speed of light that could redistribute themselves up and down the field lines, and it took no work in his model to compress the cosmic ray fluid. And that's why the adiabatic index for the cosmic rays does not appear in this stability condition. And regardless of the details, there was kind of an enduring message of this classical analysis. So I call this model Classic Parker. It set an upper limit to the fraction of hydrostatic pressure support that can be provided by magnetic fields and cosmic rays. It says if the magnetic and pressure support exceeds some threshold, the system will be unstable. And we can think of this as kind of analogous to a Rayleigh-Taylor instability, where light fluid does not want to support heavy fluid. And as far as what the actual stability criterion is, what the limit on magnetic and cosmic ray pressure support is, that depends on the compressibility of the interstellar medium. And what makes this complicated is that the thermal gas is not contributing only thermal pressure, it's also contributing dynamical pressure. So you need to understand, to determine the compressibility of the interstellar medium, how turbulence responds to an increase in density. A couple of observational facts. So when Parker did his original work, giant molecular cloud complexes, which are very cold, had not yet been discovered. And the hot gas, supernova heated gas that fills the interstellar medium, had not been detected either. So the interstellar medium, as we now understand it, is rather different from what it was assumed to be in the 1960s. And all this work has been done on cosmic ray physics. But these are really just details. The takeaway message endures, and it's been applied not only to galactic disks, but also to magnetic field generation in accretion disks. And as you heard from Rainer Beck, it can play a role in the galactic dynamo as well, in the expulsion of magnetic flux and magnetic helicity from the galaxy. So let's drill down and look at some of these effects. So I apologize if you cannot read these growth rates, which are in terms of basically a free fall rate in the gravitational field. This is a contour plot versus wave number of growth rates in classic Parker. So classic Parker means that the cosmic ray compressibility is set equal to 0. And so just for reference, this is 0, this is 1.4. This is what happens if you treat the cosmic rays as a relativistic fluid that is frozen to the gas. So this would be confinement by extrinsic turbulence with a very small diffusion coefficient. The cosmic rays are really stuck in there. And only this tiny pocket of the interstellar medium of conditions is unstable. And this number here is 0.015. So the growth rate is very slow, and most of parameter space is actually stable if you include cosmic ray compressibility. But what if you put in cosmic ray streaming? So here's classic Parker again. And here's what happens if you assume that the cosmic rays are streaming at the Alfvén speed and that their gamma is again 4/3. So this includes both cosmic ray compressibility and cosmic ray transport due to streaming and heating. And more of parameter space is unstable, and the growth rate is faster. So these details of the plasma physics are actually very important in this large-scale instability. We have to get it right. This is a large part of how I spend my days, trying to get this right. Then you can put in radiative cooling. That's an important effect too. This is classic Parker with cooling, very unstable. This is modified Parker. In other words, Parker with including cosmic ray compressibility with a gamma of 4/3. And again, you have a larger region of stability, but the growth rate is slowed down. And if you include cooling in the analysis that you just saw, then again, the cosmic ray heating doesn't do as much because the gas just cools again. And so that big patch of instability is stabilized. So again, the importance of including the physics and getting it right. So that was just linear theory. And we also did some nonlinear simulations of what we hope is a more realistic system. So we put in a better model for the gravitational field. We implemented radiative cooling, and we included diffusion as well as streaming. We didn't do everything. We didn't do rotation, self-gravity, or stellar energy input, although we're doing that now. And so this is the 2019 version of Parker's cartoon. You can see the arched field lines. So a lot of computer time went into generating this. Here are the field lines. This is the gas density. You can see that there's been some collection in the pockets near the galactic plane. This is magnetic pressure. You can again see I call these dental X-ray pictures, and you can see the effect of heating. And in this particular slide, we did not include radiative cooling, but you actually produced quite a bit of hot gas. This medium was originally at about 10 to the 4 K. You can do statistics on these models, and what happens in the evolved state is that the magnetic fields and cosmic rays really do fill out a denser, a fatter layer. So what the Parker instability has done, although it takes a while, it takes about 500 million years, is the magnetic fields and cosmic rays have moved up away from the galactic plane, creating a thicker layer, and the thermal gas is left behind. And diffusion as well as streaming can bring this about. The key thing seems to be the transport. So Parker's instability has, in an average sense, averaged over the galactic plane, worked as advertised. For comparison with observations, we did some work in 3 dimensions. So now you're looking down. We didn't simulate a whole galaxy, we just simulated a patch of it, but now you're looking down on it. And what this shows is that the instability, which we actually knew from analytical theory, that the instability has a very short wavelength in the direction parallel to the galactic plane, but perpendicular to the original magnetic field. So I actually annotated my talk and referred you back to Rayner's talk, because they may have actually seen this pattern of reversals in Faraday rotation. So this is exciting. You can also look for the effect of cosmic ray heating, which is a test of which confinement model is present. So this is a thermal phase plot. So the color represents how many cells are at that density and temperature, and the yellow represents hot gas, which wouldn't be there if not for streaming by heating. And if you neglect radiative cooling, which of course you shouldn't do, then there's even more of it. So we're hoping that something like the Faraday rotation maps and the thermal phase plots can be used as observational diagnostics to shed some light on whether Parker's instability is there and what cosmic ray transport model is being followed, if any, of the ones we have. So it's often said that cosmic rays destabilize the interstellar medium because they're buoyant. But you don't really see that in these models with constant alpha and beta. So they puff up the layer, and then what determines instability is how compressible they are. And if you treat them like a gamma equals 4/3 gas, they're really quite incompressible. They stiffen the medium, they reduce instability. So is there a way to kind of drill down and isolate the effect of cosmic ray buoyancy? And this is some work that Rourke Habiger, another graduate student in my group, is doing. And this shows so we used a scalar dye as a passive tracer. This shows the effect of injecting cosmic rays from a supernova remnant on the equilibrium of an originally just plain stratified medium. And so what happens is you set off this blast of cosmic rays on a magnetic flux tube, and they push the gas out of the way. So the cosmic rays start flowing away down the field lines. They push the gas with it, and they heat the gas, which makes it even more buoyant. So this partially evacuated tube, which remains in pressure equilibrium with its surroundings, begins to rise. And so this is what happens after 100 million years. It was originally down here, now it's up here. And we're sort of trying to quantify this effect, see how it scales with the injected energy. This is a single supernova. We're also working with clustered supernovae. And what we're trying to do, I think the bottom line is, can we speed up the time on which Parker-like effects act? Because in 500 million years, a lot of things happen in a galaxy. It goes around twice, the star formation rate can change. Although the instability, as I said, works and does in principle what it was advertised to do, it does it very slowly, and other things are happening too. So to summarize, when you go back and include modern theories or modern treatments of cosmic ray transport, the instability still exists. One of my motivations for pursuing this was looking at models of cosmic ray feedback in which the cosmic rays were frozen to the gas. And they're actually very effective in suppressing star formation because they reduce the mean density in the galactic plane. You saw this in a cartoon when I started talking about the Parker instability. But if you include streaming and you include diffusion, the instability is enhanced. And it's even more enhanced in the streaming model because of the heating. And on these half a gig a year timescales, the instability does produce dense pockets of cold gas and a thicker layer, which we can maybe think of as galactic halo, that's dominated by non-thermal pressure. So in that sense, it works as advertised. And these are some important unsolved problems that I'd like to leave you with. Okay, I've seen the chat. I see I don't have all that much time. We need to understand the growth and damping better in a more realistic background medium. That's important for estimating whether cosmic rays are well confined, how much they heat the thermal gas. We really need a full theory of diffusive propagation, what the diffusion coefficient is, how much diffusion there is perpendicular to the magnetic field, and we need to do more on propagation in a clumpy medium. So again, this was all started by Gene Parker, and it's left to us to finish it if it's ever finished. So thank you.